is Shalina Lamb, and this is Lab 2, Projectile Motion. The purpose of this lab is to analyze the trajectory of an object moving in a projectile motion and replicate it in a computational model to observe the effects of gravity and drag on projectile motion. This will be accomplished using Tracker and GlowScript. The physics behind this lies within Newton's second law. This is because we can see how forces individually act on a system and what happens when they are summed together. The total net force will change accordingly, which alters the velocity and position update formulas, leading to a different projectile motion. The gravity force only acts horizontally and downwards. The drag force affects both vertical and horizontal components. When we add these two forces together, we get the net force, and in this lab, we were able to see how just gravity affects projectile motion, which ultimately makes it go further, and how gravity plus drag can affect the trajectory of an object, which ultimately makes it go a shorter distance. Here is the video of my projectile motion being analyzed in Tracker. I use a loosely wadded up paper ball, which is the system in this experiment, and threw it like a projectile. The surrounding is everything else that interacted with the paper ball, such as the different forces or the ground. Tracker compiled the data using the centers of mass I chose and produced a table and graph of the trajectory. Using the data from Tracker, we can extract necessary information to set the necessary conditions for the computational model. Using the first point at 0 seconds, we get our initial position. Then, using the first and second points, we get our initial velocity. Our delta is 0.033 seconds, which is the time between frames of videos. Finally, the entire projectile took 1.033 seconds. As you can see in the panel on the left, using the initial conditions from Tracker, I was able to edit the starter code to model my experiment. The strength of the gravitational force on Earth is always 9.8 newtons per kilogram. The only thing we change is b, which is our proportionality constant, which I experimentally found to be 0.005 to closely match our observed trajectory. This is our model of gravity with drag, but if it was just gravity, then b would just be 0. Inside the calculation loop, we updated our FNet by separately calculating the gravity force and drag force according to the equations I mentioned before and added those together. This is vital because then it is used in the velocity and position update formulas. Lastly, I updated the way the arrows look to help me better visualize the trajectory in the computational models. Here's a video of my GlowScript code and what I saw when I ran the code. As you will see, the arrows help visualize the trajectory, and the code produces many different graphs, such as velocity versus time, but the graph we are most concerned about is the trajectory of the object, y versus x. Finally, after gathering all the data points from Tracker and GlowScript, we were able to produce a graph comparing the observed trajectory, predicted trajectory with just gravity, and the predicted trajectory with gravity and drag. The predicted trajectories both go further than the observed trajectory, and some points are negative. The predicted model without drag, however, goes much further x than all the other trajectories. The predicted model with drag just barely goes further than the actual trajectory. As we can see, drag has a much larger effect in real life than the model predicts. Also, the maximum height is larger in the actual trajectory than both predicted. As you can see, the predicted model with gravity and drag doesn't exactly match, and this can be due to a few sources of error. The center of mass that I chose in Tracker might not actually be accurate. There are a few times where the ball blended with the background and it was hard to see, so it might not be the most accurate center of mass. Also, the drag coefficient might not be the exact one, but I just had to guess the closest based on looking at the different graphs. Also, the initial velocity that we calculated might not be the actual one, since this is just an experiment after all, and there's limitations to the accurate information we can derive. So what does this mean? Do any of my models predict a terminal velocity? No. Even though it might seem like the x component of the velocity without drag is terminal, the y component still changes, so it is not a zero net force. The only reason why the x component doesn't change is because gravity only acts on the y component, but the total net force of both of them would still be non-zero. To actually model terminal velocity, we would need a lightweight object that experiences large drag, and we would drop it from a much taller height so that it can reach constant speed and actually show terminal velocity. What if the object was thrown straight up with the same initial speed? If this occurred, then the object would take longer to reach the floor since it would only be affected vertically and not horizontally. The full speed and energy would only be going towards going up, which would make it go higher, meaning it would take longer to go down. Thank you for watching.